So welcome everyone, I'm Guilherme, and this is creating a large dataset for pre-training LLMs. So just a quick overview of what I plan to talk to you about today. So first, just an overview of the multiple steps we go through when we create an LLM, why data matters, why do you need so much data, because you've probably all heard that these models need a lot of data to be trained on, what is actually good data, and then some actual data processing applied to an example, the dataset I worked on, FineWeb. So first, a quick overview of large language models, or LLM for short, training stages. So there are multiple stages. Usually the first and one of the most expensive, if not the most expensive stages, is the pre-training. So this is the stage where we're giving a lot of different generic data to the model, so that the model can basically perform any sort of general task. Usually this is followed by some sort of instruction tuning, so you want models to actually obey to instructions and not just spit out random chunks of text. And then there's an alignment stage, right? And this alignment stage can be less or more costly depending on who's doing it. There are some rumors that, for example, OpenAI spends a lot of money on this step. And there's some other stages of learning that are not as expensive. And each stage has a different goal, right? So we want different things and different types of data for each stage. Now, why data matters? So this is a famous blog post I made around last year from an OpenAI engineer. And basically what he says is that so far, he's been at OpenAI for a while, he's test trained a lot of models, and what he has come to realize is that at the end of the day, the thing that really matters, the thing that really makes models better or worse, is not so much all this amazing new architecture or new optimization thing you come up with, but more so the data you use to train these models. And people usually focus more on this architecture side, and it sounds more interesting. You come up with this amazing new small change that will improve everything. But at the end of the day, it's hard work on data that will make a model really, in the end, much better. But why do we need so much data, right? Because you've probably heard we need a lot of data for these models. So this is there's something called scaling laws. So you might have heard of them. Basically, they tell you, okay, you have X amount of hours you can spend on a GPU cluster. So you have a certain amount of dollars you can spend on this training. We want to train the best possible model we can with this budget. So how do we choose the size of the model and then consequently the size of the training data set we are going to train this model on? And in 2020, so this is from an OpenAI paper, there was this idea that as you scale the compute you have, so as you have a bigger budget, you should scale a lot the size of the model. You should train a much bigger model, and you should scale a little bit the data set. Okay, so what happened is people were training these huge models on not so much data. So you'd have models with 100, 200 billion parameters trained on less than 1 trillion token, which for today's standards sounds quite weird, and you'll see why. Basically, there was this other paper in 2022 from DeepMind called Chinchilla, and the thing they said is they tried to get new scaling laws, and they concluded that models were under-trained. So basically, the scaling we're doing on the size of the models was way too big for the small increase in dataset size, and you should actually be scaling the dataset much more. And so to prove this, they trained a model called Chinchilla on the same compute budget as the Gopher model. So you can see they have this is the same number of flops in the end, okay, to train these two models. And you can see Chinchilla is much smaller and trained on much more data. And in the end, they proved that Chinchilla was much better than Gopher through these scaling laws. So people started training, now you need more data because you realize people were under-training models. And then there's another thing that kind of changed the game recently. As you might have heard, models are starting to get smaller and smaller. And even some people want to deploy them on mobile devices and so on. So you have limited memory. You need to scale down the size of the models. And deploying very large models is very expensive because they need very big dedicated GPUs, right? So obviously the inference cost will go up in model size because you need more GPUs to serve this model. So what people started doing now is, so we went from under-training to the Chinchilla optimal value to now over-training. So you take a much smaller model and you train it for much longer, even beyond the Chinchilla optimal size, right? So now we need basically at least a few trillion tokens, even for these very small models, which is why we need a lot of data. And you can see, as an example, you might have heard of the Llama models, most recently the Llama 3.1 model, and even the smallest of them, the 8 billion parameters model, was trained on 15 trillion tokens. And if you recall the slides before, people were training on not even 1 trillion before, and much bigger model parameters. So this is the new age of large language models. We have slightly smaller models trained on a lot of data. So what is actually good data? Because, okay, so you need to make a big data set. You want it to be good, but how do you know what is good data, right? So it's not hard to define. Okay, so it's a kind of an open question. So there are a few things you could try. You could have like a qualitative approach. You can try looking through data yourself. You'll be there for a few thousands of years, maybe. And like maybe you can just check the top domains in your data set. You can try to use some sort of more manual checking. It's, always good to do a little bit in the end. Or you can do other approaches. So for example, you can train a model on some gold standard corpus. People are doing Wikipedia for this. And then you could check the perplexity, so basically how similar some data would be to this reference corpus the model was trained on. So you basically be checking how similar something is to Wikipedia. It also has some drawbacks. And there's this other approach, which is a bit more costly because it involves you training models just to detect what is actually good data. And this is the approach that people now at like the top labs go with. And you have two approaches. Basically, you train a model on the data set you want to test, and you basically take a bunch of large language model evaluation tasks, and you test this model on these tasks, and you see how it does, and then you compare it with some other model trained on a different data set. A different approach as well is this leaderboard kind of chatbot thing. You might also have heard of this LM-sys leaderboard. Basically, people try different models and compare side by side and choose which one is best. This is also quite difficult to do because then you need, you can't just change one thing in the data set, train a new model, and submit it to the. It's just like not doable, right? So the main approach people do is this: you train a model, you evaluate it on benchmark tasks, you get a number in the end. Numbers goes up, data set is good. Okay, but then what are the tasks you use? So it's actually hard to do as well because you optimally will not be training very, very large models unless you're very rich in compute. You'll be training somewhat smaller models. So for instance, people usually do 1.45 billion parameter models, train around 30 billion tokens or giga tokens, and then we evaluate them on some tasks. So we kind of want tasks to be well-behaved, because for some tasks you need a very large model to be able to get any results, otherwise you just get random performance. So you also need to be careful with how you select tasks. And I give you an example, so you can see two tasks here, and we are evaluating the same models, okay? And you can see, like here, the performance just keeps going up, and it's more or less stable. And here's just like a big mess. It's very hard to say which model between the purple and blue lines would be better. So this task is actually quite well behaved. And this is more or less the sort of task you would be looking for. Okay, so now on to some actual data processing. So we've gone over why you need a lot of data, why data is important, and what kind of constitutes good data. But then how do you get this data? How do you process it? How do you actually create a very large data set? So as I mentioned before, for pre-training, you kind of want a very generic model. So you want a model that can do any sort of task, and that can even be further specialized later on during the fine-tuning stage. So we want massive quantities of very generic text. So obviously, might come to mind to you that a very general place in terms of data is actually the internet in general. And we'll get to that in a second. But so there are a few challenges. We've actually mentioned a few of them. So how do you evaluate data? What is good data? How do you actually get this data? The robustness of things, like how do you actually scale this to a very large processing pipeline and everything? Coverage, so you want, as we mentioned, a very wide coverage, very general data. And maybe you actually want to be careful with some biases you might be introducing as you are training. And then actually the engineering challenges as well. So for sources, so where can you get a lot of data? So as I mentioned, one good place is the internet. And there's this thing called Common Crawl, which is basically a publicly available data set, very large data set. They've been crawling the web since 2007, something like this. And they just, every month they release a big dump. This is the internet for this month. Obviously not the full internet, but a large chunk of it. And this thing is really huge. You have petabytes of data on this. And most people start on this, at least even OpenAI, for example, when they were saying what they were doing, they were using Common Crawl in the early days. You actually have code as well, because now you have all these models that are good at code. Maybe you've been using, I don't know, Claude or some other model. Usually GitHub is a good place to get code, makes sense. And you have some more created, usually smaller data sets, such as Wikipedia. You can just drop Wikipedia in your training data sets, and also books, where some people will try to use public domain books. Some will not be as careful and will just dump all the books they can find on the internet on the pre-training data. You have also some more recent trends. So for example, some people have been using synthetic data. This means that you have a model generate some data for you that you then in turn use to train another model. And this works well for some big models and in specific contexts. So high-level view. So we have some data. Possibly, let's say we take common crawl, so web data in general. What we actually do with this data. So there are two main things. So a first step, which is, in this case, we have web data. We want to extract the text in this HTML data. But then there's a second stage where we just filter things. So we have too much data. We want to remove a lot of trash. As you might imagine, the internet has a lot of trash in general, a lot of adult websites you maybe don't want to train your model on, a bunch of spam keywords to just get search results optimized. You want to throw all of this out. And then also some deduplication, because also a lot of websites are just copies of each other. They take chunks from here and there, and then it's just not efficient to give the same data over and over. So basically, you take your data, you do some filtering, and you deduplicate it. So what sort of things can you do? So as a first step, just to explain what I was saying, so like, for example, you take some web page that has this HTML content. In the end, the only thing you care about is hello world. That's the only machine, like the only natural language you actually have on this page. So you need some sort of way to format and extract it from the raw HTML. And even Common Crawl itself, they give you a few formats. One of the things they give you is a version, which is already extracted. And you can see it's much smaller. So this is for a particular month only, right? So it's not the full thing. It's just 1 month of Common Crawl has around 100 terabytes raw HTML data. You can take their version, which is not that well extracted, because it keeps a lot of like navigation menus, things you don't really want. Or you can use some other library. For example, we use usually a library called Trafilatura. You just take these 100 terabytes and you extract all the useful text from these pages. Then you want to do some filtering. So if you're training, for example, an English model, or let's say as an example, a Portuguese model, you don't want to give it Spanish, English, and so on. So usually people use a small model that can run on a CPU, because again, you want things to be very scalable. And you just give each text to this model and it will rank based on the language it was trained on. Okay, there's a high probability this is Portuguese. We will keep it. If it is not, then we will throw it out. And then there are more like handmade kind of statistics. So these are not super easy to come up with. Basically, you had some person at some point in time that went through a lot of data manually and decided, okay, I don't like things that mention JavaScript because they are usually enable your JavaScript content things. We don't want to train on this because there's too much of them, so people add a rule. If something mentions JavaScript, we throw it out. As an example, there's a lot of different options. You can have things such as, okay, this looks like a list of keywords, we throw it out. This is just repeated content all over again, a lot of symbols. The entire text is capitalized. Many different options for this. And people test these things. Now people have started to actually test it also with models. Before, people would just like, okay, kind of vibe check things. Okay, this looks good. Let's just throw out things that mention lorem ipsum, for example. So some advantages, they are quite controlled. You know exactly what you're doing. You're just throwing out text that mentions JavaScript. But there are some drawbacks because it's very surface level, right? You just don't go too much into the content. You just check this one thing, you remove it. And there's always a danger of removing too much. If you remove everything that mentions JavaScript, you will likely remove all the JavaScript tutorials from the web. So then if you ask your model, okay, can you show me some code in JavaScript? Maybe it won't have any, right? Because you just removed it all. So you need to be careful with these things. And usually set a threshold for some of these. So like if you have a ratio, you also need to tune them a bit manually. As an example, for what we were developing on FineWeb, we had this metric, which was the fraction of lines that ended with punctuation. And we were comparing two similar data sets that had different quality. And we knew this because we trained different models on them. And you can actually see there's a big difference there. On the lower quality data set has a higher frequency of documents with this metric below a certain threshold. So we just added a new filter. Okay, let's remove anything that has the fraction of lines and punctuation below 1.2 or 3 or whatever it was. So this is a way you can try to come up with new things. Okay, so there are other options. You don't have to do this very manual, annoying work. You can also actually do some ML-based filtering. And there are a few different options as well. So you can try to do something to distinguish between dirty and clean data directly. So GPT-3 did this, like their training data has a small fast text or BERT model, I can't recall, that would be trained on some dirty data and some manually created clean data, and they would use this to directly filter what to keep and what to remove. You can try to find data. So this is a more recent approach. You can, because people want these models to be able to follow instructions well. So maybe you could even use that for pre-training a little bit instead of just leaving it for instruction fine-tuning. And you can train something that will find instructions or things looking like instructions. This is the approach from the DCLM recent datasets. Or from my own work, you can do something like on FineWeb Edu, which you basically train a classifier to say how educational some content is, which also has its own challenges. And for this you can use, so for example, for the dirty and clean approach, you can use just filtered and unfiltered common crawl data. You can try to generate some examples, so synthetic data sets. And you can also use model-generated annotation. So for example, for the educational classifier, what we do is we ask a model, how would you rate this based on a big prompt? And then we train a classifier on these labels. There are some issues with the ML-based filtering. Usually you have introduced some quite strong biases, and you can lose some coverage or diversity, which depending on your use case, usually if we are doing just pre-training, we don't want to lose any coverage, and we don't want the model to not be able to do specific tasks. So we need to be very careful with this as well. Then we have deduplication. So basically, I mentioned this before a little bit, but you have a lot of duplicates on the web. So you have a lot of web pages that will just copy. They are aggregators. They are you have a URL which will serve the same page, but it's actually just two different URLs. And these will all be on Common Crawl or some other crawled source. And it's just not efficient. It's not good to give the same content over and over millions of times, sometimes to put them in your training data set. It actually also harms memorization, so models will tend to memorize things you give them very often, and then if something kind of looks similar, it will just spit out this text. And sometimes the main issue, I'd say, is these very big clusters, because you have, let's say, one example, you have all these websites powered by WordPress. There was this one WordPress plugin that had some text plugin developed, blah, blah, blah. This thing was repeated millions and millions of times on a common crawl, on each common crawl dump. So you were just training a model to know that this specific WordPress plugin was developed by this specific guy many, many times and wasting your precious compute budget. And it's also been shown that if you deduplicate, you improve accuracy on downstream tasks. So how do you deduplicate? There are many different options. I won't go too much into the details here, but you have mainly fuzzy methods. So basically, you try to find things that seem similar. So you have mostly min hash is used, where you hash things and you get a signature for each document. Then you compare them. Some sort of semantic or embedding-based approach, where you find similar documents based on their embedding. Then you have more exact methods. This is more like classical things with suffix arrays, just taking all the URLs and duplicating on that level, or even things like line deduplication, where you hash each line, then you find matches, and so on. So there are many options you can take here on these things. So even the method, and each one has their own thresholds. There are all these trade-offs, like this is usually the most expensive step of creating a pre-training data set, for one simple reason. Before, we had something that was fully parallelizable, right? You're filtering, you look one document at a time, you decide if you keep it or not. Here, you kind of want to look at matches between documents. So you need to have some sort of big aggregate step, and this will make it very expensive if you have a very large data set. And there are some other considerations, like should you just duplicate your entire data set, or should you do it one month at a time of common crawl data? Because there might be some signal, like usually some pages that are crawled every single month, they might be better. So maybe there's some signal there you lose by doing all this aggressive duplication. And obviously there are other hyperparameters you can tune on this sort of thing. So now I'll give you a more concrete example of a data set and how it was created. So this is the recent FineWeb data set I worked on. And this is mainly the pipeline. So we started with our common crawl data. We did some URL filtering. So we had a list of websites that things like the school library will block. So things you don't want to give to a model to train on. And we just dropped documents that had these URLs. We then did text extraction. We used the library I mentioned before. Typically you don't want to keep all the navigational menus, all things that, maybe the comment section. You just want the main content of a page, right? You don't want to share this on Facebook, message at the end. You don't want all this stuff. So just have some sort of library. They'll have some heuristics. We'll look at the HTML and keep the main sections of the page. We then did some language filtering because we were doing an English-only data set. So we wanted only English data. And then there are these filters from a paper from DeepMind, the Gopher paper, I mentioned it earlier. Basically, they have some heuristic rules, so the ones you basically make by hand, and we use some of these as well. We then use min-hash deduplication. So for min-hash, more specifically, what you do is you take your documents, you come up with a way to have a signature for each document, and then you try to group them. So let's say, okay, we have two documents, they are similar. We have another document that is also similar. We create a big cluster of duplicate things, and then we basically drop everything except one document. Okay, so you just cluster things by similarity, and then you just drop everything except one. You have some more filters from the C4 paper, another dataset that's quite old, and then we developed some custom filters. So here we did the picture I showed you before, the plot with the two distributions. This is something we did. We looked at distributions for like 30 different metrics. We took different datasets that we knew were better or worse, and we compared them. So for example, for some metrics, you'd have no difference. For some, you'd see a clear difference where the higher quality dataset would have a higher distribution on some threshold. So we would use this thing to come up with different new metrics. And finally, this is a new step that people are starting to care about a lot. I'm not sure if you've looked at some internet pages, but a lot of them have contact details, addresses, people's names, phone numbers. So it's not nice if you're just using a model and it says, okay, maybe you should call this number, and then you got to call. Actually, Claude told me to call you. Maybe it's not a good idea, so we did some steps to remove emails, phone numbers, and things we could, like IP addresses, other things you can find. So this is the FineWeb pipeline. Now, how do you actually go about, let's say you have some CPU hours, you want to create a pretraining data set for some language, let's say, because for English there's quite a lot already. So what can you do? So we have this library, an open source library, which is actually what we use for FineWeb. And it basically will take care of a lot of things for you. It has pre-built processing blocks, okay? And it's fully free to use. And as an example, this little code will fully reproduce our FineWeb pipeline. So you start, you read your data, you filter it, you run Trafalatura, you do the language filtering, you do the Gopher repetition, Gopher quality filtering, and all these filters, and then you just save it. And there's other steps for duplication. So like with these sort of libraries, you can fully reproduce. And it's a new thing people are doing, because before, a few years ago, people would sometimes share how they create data sets, and you just have this messy Jupyter Notebooks folder, which has some very messy code and very hard to track. And so it's nice that people are starting to work on this. So it's not just this library, but there are other libraries coming out of people working on this thing. We have some other tools you might find useful. So I just already mentioned Datatrove, but if you want to do training, we have Nanotron for distributed training. We have LightEval for evaluations. So this is also another big issue. I mentioned this a bit, so like how do you choose tasks? How do you run evaluations? It's not easy. Changing prompts, for example, will change completely results. We have some fine-tuning libraries and some other for inference. We have quantization and deployment, for example. We have bits and bytes and text generation inference. People now are using VLM, but a few years ago, TGI was quite big. So I kind of sped up a bit in the end, but that's it from me. This is where you can reach me.